Thank you. So this is a joint work with my advisor, Ishai Mansour. So let's start with an example. Say Alice would like to drive from Tel Aviv University to the Hebrew University in Jerusalem. And there are two alternatives, Road A and Road B, out of which Road B is usually faster. It usually takes 1 hour, as opposed to Road A that usually takes 2 hours. Now, when Alice opens up her navigation app, the navigation app tells her, you should go from Road A. Okay, so she's a bit surprised, but she follows the recommendation anyway, because the app knows something that Alice doesn't. It knows the current delays on the road. So she follows the recommendation, drives from Road A, gets to the Hebrew University within 2 hours, and later on the day, when she meets her colleague Bob, she finds out that he left Tel Aviv University at the same time, took Road B, and got into a huge traffic jam. And that cost him 3 hours. Okay, but here is a problem. In order for the app to know the actual delays on the road, it needs to sometimes sacrifice some of the users and to send them to explore the a priori slower roads. Luckily for the app, every time the users get recommendations, they are unaware whether they are exploring the a priori slower road or exploiting the knowledge from the previous users and enjoying the free road. So one thing we have to consider here is that if we would send the same user over and over again to explore the a priori slower roads, the user would simply remove the app. So our goal is to design a recommendation policy for the app that would balance the probability that each user explores and exploits. That's what we call Bayesian incentive compatible constraints. And under this constraint, we would like to minimize the accumulated delays of the users, which in this community is called maximizing the social welfare. The only tool that the app or the planner of the app has is information asymmetry, which means that the app gets to observe all of the users' delays, and every user can only observe his own private delay. So how do we model such a problem? For this, we use settings for machine learning, which is called multi-arm Bandit. In multi-arm Bandit, you can think about k different actions or arms of slot machines in a casino, and a planner, or if you like to think about it as a gambler, who selects the action with a goal to maximize the accumulated reward, which is done by balancing the exploration, finding out what are the rewards distributions, and the exploitation, gaining rewards from the knowledge that the planner already has. But, okay, so here are the difference between this setting and our problem. So first, in this setting, we maximize the accumulated reward instead of minimize the accumulated delays, which is fine because it's the same. And in this problem, the planner don't get to select the action. The navigation app, whether it's Waze or Google Maps or any app that consider actual delays, cannot simply recommend on an action and to be sure that anyone would follow in a way that would benefit this maximizing of the accumulated reward. So we have to make sure that every recommendation that is given is in fact Bayesian incentive compatible in order for the agents to follow it. Okay, so now I'm gonna talk about agents instead of drivers and about rewards instead of delays. Okay, so what work was done in the area? It started in 2013 when Kramer, Mansour, and Perry presented the model for the problem and derived optimal policy for two deterministic actions. It was So it was later extended for stochastic actions, multi-agent game in each time step, and two competing planners, which Ishai is going to talk about in Young EC on Thursday, 3:30. And our results is optimal Bayesian incentive compatible algorithm for the planner or the app that handles any number of actions, K, with somehow restricted prior, which I'm going to talk about in a few slides. Any number of agents. This could also be infinite number of agents. And we show that our optimal algorithm minimizes the total exploration time for each action independently, and as a result, maximizes the social welfare. Okay, so let's go over the model for our specific problem to make sure we're all on the same page. So at each time step, T, a new selfish agent, T, arrives. He then gets a recommendation from the planner. Say the planner is telling him you should select action number 2. Now we assume that that all the agents are aware of the prior distributions of the rewards and they're placed in line. So they can calculate whether or not it's benefit them to follow such a recommendation. They then the agents. Then agent T selects an action. It could be the recommended action if it's Bayesian incentive compatible. Yeah, it's always the recommended action in case the recommended action is Bayesian incentive compatible. If not, it could be any other action. And we assume that the planner gets to observe the rewards that agent T gets, which is exactly his utility. And then the agent lives forever. In the next iteration, this reward is gonna stay +1. Now remember that the planner knows that this is the reward for action number 2, but none of the agents to come is gonna know it. But since we do discuss social planner, when the next agent T+1 arrives, the planner is gonna tell him, you should go for action number 2. And he gets the same utility, the same reward, and so on. Okay, so let's talk a little bit about definitions. A recommendation, sigma t, is Bayesian incentive compatible if the expected difference between the utility from following it and the utility of any other action given the agent knowledge is not negative. Okay, so here is the agent knowledge. This is a sigma t, his own recommendation, his place in line, and the prior distribution for all of the rewards. And since the agents are aware of how the algorithm works, they can calculate whether or not the recommendations are Bayesian incentive compatible. So Bayesian incentive compatible means that it benefits the agent to follow. And this way, we can automatically assume that if we use a Bayesian incentive compatible policy that gives Bayesian incentive compatible recommendations all the time, then the agent automatically follow. And now if we want to calculate the social welfare of such a policy, then we simply calculate the expected accumulated utilities of all the agents. And the expectation here is over the stochastic, the stochastic of the policy. And we are going to maximize this social welfare. Okay, so I mentioned earlier that it's going to be a prior distribution. So let's consider for a moment even more restricted prior, where the case is that each action can only have 2 possible rewards, either -1 or +1. And without loss of generality, we assume that the prior expected rewards are from the a priori best for the first action to the a priori worst of the last action. And in this case, it's really simple how to maximize the social welfare. So let's say the first agent arrives. He knows he is the first in line, so he knows that there is no other information that the app can have that he doesn't. So he would not follow any other recommendation other than the first action, which is the a priori best. So he gets this Bayesian, the only possible Bayesian incentive compatible recommendation, and follows it. And now the planner can decide what to do based on the reward. So if it's +1, he's going to keep recommending everyone you should go for action number 1, because that's optimal. There cannot be any higher reward. If it's -1, then it's better to recommend on action number 2, which has the a priori best expected reward. So this is what he recommends agent 2 in case the reward of the first action was -1, and so on. Okay, so this was very simple, and today what I'm going to show you is how things are getting complicated even for 3 actions for support of -1, 0, +1. So this is all of the possibilities for reward for the a priori best action. And I'm going to leave the same support for actions 2 and 3. And we're going to discuss infinite number of agents, but in the paper you can also find a version for any continuous distribution with support between -1 and 1 for the a priori best action and any number of actions. And so the support of the other action is always either -1 or +1, and I'm going to show it for 3 actions today. In the paper you can find it for k actions. And so this is the support of the first action for today, but in the paper there is a continuous distribution, any continuous distribution with support of between -1 and 1 only for the a priori best action. So this here is gonna stay throughout everywhere. Okay. So let's consider for a moment what happens if we add the possibility to get a reward of 0 for the a priori best action. So here's the same drawing from before, and in case the reward of the first action is 0, we get some sort of tension between the planner that has infinite number of agents after this agent and would like to do exploration. So there is a positive probability that the second action would get a reward of +1, and the same goes for the third action. So the planner would like to do the exploration as soon as possible. So when the second agent arrives, she would like to recommend him go for action number 2. But on the other hand, if the second agent would have known that the reward is 0, he would not. He would prefer to select action 1, get a reward of 0, instead of selecting action 2 and risk a negative expected and get a negative expected reward. Okay, is it clear? Okay, so what would come to our rescue? So this is the information asymmetry. Luckily for the planner, the agents are unaware of the realization, and even though the reward here is 0, the agent cannot know whether it's 0 or -1. So he knows that if the reward is +1, he's going to get a recommendation for the first action, but if it's -1, he's going to get a recommendation for the second agent for the second action. But if it's 0, we can still recommend him go for action number 2 with some probability in a way that it would still be incentive compatible. Okay, so how do we design this optimal policy? So we start by doing an abstraction. The only information that the planner needs is the time step t, as well as the realizations of the rewards if this reward has been sampled, and we mark stars for the actions that hasn't been sampled yet. And so as I've showed you, we already know what to do if the first action has a reward which is different than 0. So if it's the case that this is the information state that we get into, then what we do is we calculate the maximum exploration rate, which is the maximum probability the planner can recommend action J to agent T. We mark it by QJT. And this probability still holds the Bayesian incentive compatible constraint. Okay, so we maximize this probability for all the agents and all the actions, and we have these Qs. Okay, so for example, Q32 is 0 because there's no way the second agent is gonna follow recommendation for action number 3 because he knows he's the second in line, and there's no way the planner already observed both action 1 and 2. Okay, but now how do we use these Qs to give recommendations? So here's a suggestion. If we are in an information state that requires us to do to give exploration recommendations to explore actions, then we can simply recommend action J to agent T with probability QJT independently. But what would be the problem in this case? So if it's all done independently, then it could be the case where agent 3 is selected to explore both action 2 and 3. And if that's the case, we would have to, since we only have to recommend one action in each time step, then we would have to skip it. And we want to get an optimal policy, optimal algorithm, so we don't want to do it. So instead, we want to maximize all the exploration rates at the same time and use this maximum exploration rate at once. So for this, we use a randomization technique to choose who should explore each of the actions in case the first action has a reward of 0. Okay, so now we show some properties regarding these Qs. So for example, the exploration rate of the third action for agent T is always smaller than the exploration rate for action 2 to agent T minus 1. Then we can, so this is what we have here. The action 3 start with agent 3, action 2 start with agent 2, and then we can simply sample a single parameter y from a uniform distribution between 0 and 1, and this allows us to avoid collisions and also to guarantee that the exploration order is done according to the a priori best to the a priori worst. This nice theorem here also gives us a result that if the number of agents is large enough, then the policy reaches a terminal state, which means that he would either discover all the rewards or find an optimal reward. And later on, we show that this policy is stochastic dominant over any other Bayesian incentive compatible policy. So it means that in every time step t, the probability of this policy to discover the reward for action j is not less than any other policy. And this is required from the optimal Bayesian incentive compatible algorithm. So this is in fact maximizes the social welfare. And so this is it. So to sum up, the results are for two different supports for the a priori best action, either discrete or continuous version. It handles any number of agents and actions. In both settings, it explores the a priori actions, better a priori actions earlier. It maximizes the exploration. It requires the special correlated randomization. And if there is a large number of agents, it would be guaranteed that we reach a terminal state. As for open problems, so three directions are either to extend the support of all the actions to be between -1 and 1, or to consider stochastic actions, even a simple Bernoulli random variables with different probabilities, or to enable agents to receive some limited information about the past. So here the policy doesn't discover anything about the realizations of the reward, but one might consider this nice modification. Okay, thank you very much. Questions?
So it might be the case that you said that and I missed it. To which degree depend your results on, let's say, the first agent knowing that they are the first agent?
I always assumed. So
do you have any idea what would happen if you drop that assumption? If I'm thinking about, let's say, my random app, I usually I'm not the first one, and I also don't know.
Right. So it would make things a bit easier, because then you can consider there is this isn't like another constraint